Professor Pecker, yeah, Professor Song, and ladies and gentlemen, professor, students, good morning. My name is Jacob Huang. I'm the acting director of IAS CEU. So welcome this morning to our event, and we are very honored to invite Professor Pecker all the way from France to give us a distinguished lecture. And I just examined his biography, and it's really, really amazing. He's not only a professor, he is also the founder and also the president and CEO of a very special solid mechanics laboratory and in a company named Geotechnology Engineering Company. But he retired in 2015. Why? You're so young. Huh? Yeah. But he has been also the professor both in Paris and France, and also in Pavia in Italy. And he just mentioned to me he had to teach in both institute, and in Italy he had to teach a very intense short course within 1 month. So maybe we can try here. So we have a IAS special course for 1 month. So you have to come here during the summer and get 5 hours lectures per day. Oh, that's not easy. Yeah, and he has been professor from 1974 until right now. So, and I would just inform that Professor Pecker was the student of Professor Alain, right? Yeah, so you are the teacher's teacher. Yeah, so very impressive. And also Professor Pecker is the chairman or the member of many important scientific committee in France and in Europe. And also he is the member of French National Academy of Technology. Okay, and most of Professor Pecker's research are dedicated to soil dynamics and the earthquake engineering. Yeah, I think this is very important. Probably not in Hong Kong, but it should be very important in some other country. I'm sure if you are giving a talk in Japan, probably this attract the whole crowd. Yeah, but Hong Kong, we seldom have earthquake. Yeah, I've been here for a while, but I had never experienced an earthquake. But in my country, we have earthquake every week. So so we really need you. And also, he introduced a very important notion of capacity design as a new theory, very important for civil engineering. And recently, he established the new formulation of nonlinear soil structure and for architecture design. I think that will be related to today's talk. So Professor Pecker will give the talk on research and practice in engineering, the Rion-Antirion bridge foundation design. So let's all give a warm applause to Professor Pecker.
Okay. Thank you very much, Professor Wang, for your kind introduction. And before starting, I would like to thank the Institute for Advanced Studies for inviting me to give that lecture, and also Professor Salençon for suggesting my name for that lecture. And as you will see from my talk, the contribution of Professor Salençon is more than suggesting my name, and most of the work that I will be presenting would not have been possible without this close collaboration. So what I will try to do in my talk is to show how research and practice can benefit from each other. And I will show that on a practical example of the Rion-Antirion bridge. In my mind, practice uses, of course, the scientific achievements of research, but research can maybe be inspired by practical issues. So the example I've chosen is the Rion-Antirion bridge in Greece, and This bridge is located here near the town of Patras, which is 250 kilometers west of Athens. And until the bridge was built, the liaison between the Peloponnese in the south and continental Greece in the north was assured by ferries, which is not very convenient because, as you can see from the map here, all the lines here are the main roads in Greece, and it's a very important liaison between south and north Greece. Okay? So that bridge was awarded to the French company Vinci with Greek partners, of course, and it was awarded under a concession contract, which means that the company has to finance the project, design it, build it, and then it will own the bridge for 34 years in that case. It will operate the bridge, and at the end, they will transfer back the bridge to the Greek government. With that in mind, what I will try to show you is a quick overview of the project, and then we will focus on the geotechnical and environmental conditions, which really make the challenge for the construction of the bridge. I will describe what we have adopted for the foundations, how we designed them, what we implemented, and then I will conclude with pictures of the site during construction, which are very impressive. And at the end, I will ask a last question. So some key dates. The tender for the bridge was launched in 1992. The contract was awarded in December 1997, which means that during 5 years, there were discussions between the contractor and the Greek representative to convince them that the bridge was feasible. Then the construction started 2 years later, in December 1999. And you will see that these 2 years, of course, we are not inactive during 2 years, and we will see that it's very, very important. Then the bridge was completed in August 2004. You will see also why. And the total cost of the bridge, including all the financial issues and so on, is 770 million euros. 630 are for construction. Okay? So this is the bridge, right, almost completed here. So this is the Gulf of Corinth. We have here on the south part of the Peloponnese with the small town of Rion, and on the north part, the small town of Antirion also. The bridge is a multi-span cable-stayed bridge, which each span is 560 meters, which makes the total length of the deck 2.2 kilometers, a little bit more. And when I'm mentioning 2.2 kilometers, you will see also this is an important issue in the project. Another view of the bridge from the Rion side, from the south, and you have four main piers here. And if you look at one pier, you will see how unusual are the dimensions. The total height of the pylon is 230 meters from the bottom to the top. You have here 65 meters underwater, which is quite unusual for a bridge, 55 meters from the water level to the deck, and then another 110 meters to the top. But now if you look at the foundation, you see that there are footings which are 90 meters in diameter. It does not mean anything for you, but if you think, for example, if you look at a soccer field, this is exactly the size of a soccer field. So we have four soccer fields underwater here. To give you some figures, the weight of one pier, I mean the buoyant unit weight, given the 65 meters of water, is 750 meganewton. And this foundation will be subjected to forces due to the earthquakes, which are around, let's say, 600 meganewton for the shear force at the foundation level, and another turning moment of approximately 18,000 meganewton meter. This gives you some figures for the bridge. So let's now have a look at the environmental conditions. First, the geotechnical one. So of course, we conducted a lot of site investigation. So you have here a cross-section through the strait. This is the south part, the north part. And what we found within the investigated depths is only weak materials. Alluvium consisted of sand, gravel, clay, silt, in alternating layer with absolutely no rock, and we know now that from the geological studies and geophysical investigation that the rock is deeper than 500 meters. That was the first challenge. Second one, if you look, okay, we are not in Hong Kong. This is one of the most active part, earthquake active part of Europe. This is the Gulf of Corinth, you see here. Athens is here, Patras is here. And the Peloponnese and the continental Greece are pulling apart at a rate of, let's say, a little bit less than 1 centimeter per year. And that creates a grabens here, which is the Gulf of Corinth, with all the red lines being faults. And it turns out that the seismic hazard at the bridge is governed by this fault here, which is a Satopyrgos fault, which is only 8 to 10 kilometers away from the bridge. With that, the seismic condition we have to take into account is an earthquake with a magnitude of 7, a peak ground acceleration at the seabed level of 0.5 G, and this earthquake has a probability of incidence of 0.05% per year, which is a little bit of the order of 5% in the lifetime of the bridge, which is 120 years. In addition to that, since we are in an active area, the government required that we take into account tectonic movements, and this tectonic movement were specified as 2-meter displacement, either in the vertical or in the horizontal direction, and between any two piers of the bridge. We have to take that into account. And finally, it's a strait where cruise ships are traveling, and a ship impact of this kind of ship here traveling at 16 knots has to be taken into account. And the forces induced by this impact are just a little bit less than the earthquake forces. Okay, so if we try to summarize, the challenges for the bridge were the following one. No rock formation at a depth less than 600 meters. Very large water depth, 65 meters, and performance objectives. This is what we expect from the bridge after the earthquake, which were very severe for this 2,000-year return period event, which states that the damage are acceptable, but after the earthquake, the bridge must be repairable in order to be reused. So it was translated, this condition here, into design conditions, which said, okay, we can accept sliding of the foundations, which is a new concept. It was not usual at that time. So we can accept sliding. In any case, the bridge should be capable of withstanding 2-meter displacement. So we can accept some displacement. But of course, we will prohibit any tilt, because with such a high pylon, any tilt will be detrimental to the behavior. So with that in mind, we tried to design the foundation, and of course, we went through all the possible means for the foundation, like piles, embedded caissons, even soil substitution below the foundation, because I did not mention, but the top 20 meters are really weak materials, and shallow foundations. I don't have time here to go into details, but I can answer questions. Very quickly, we just disregard the first 3 solutions because they were too costly. They were not very efficient, and we said, okay, the only possible solution would be shallow foundation. Shallow foundation have many advantages. They can be constructed quite quickly. They are less costly than any other type of foundation. But of course, what could be the behavior of such shallow foundation on weak materials? So we went through examples, and hopefully we have a lot of examples of the behavior of shallow foundation resting on soft soil condition from post-earthquake observation, and I will show you only 2 examples in Mexico City back in '85, or in Loma Prieta in California in '89. And I will not show examples here, but all these observations were also confirmed by model tests in different facilities with different testing facilities like shaking table tests, centrifuge tests, and so on. Okay? So just one example here in Mexico City. This is a 4-story building which is founded on a raft at the ground surface. And you see this picture. I took the picture 2 weeks after the earthquake. And you see that the building has tilted a lot to the west here. And we will go on the left side of the building, and this is the entrance of the building after the earthquake. Of course, architects did not design the entrance like that. And this is a result of bearing capacity failure of the foundation. Another example, again in Mexico City, an isolated footing that punched through the ground because of the loss of bearing capacity. In Loma Prieta, just to give you another earthquake, it's not specific to Mexico. This is a gas station with, you see the pipelines here, which were founded on concrete block on the field here. And you see that during the earthquake, the field settled a lot, and all the pipelines lost their support here, and by, let's say, 20, 25 centimeters. So, shallow foundations were attractive, but of course it cannot be used like that. It's totally impractical because this kind of disorder may happen after the earthquake. So we said, okay, let's try to do something. Let's try to use shallow foundation, but to improve the soil below the foundation. Okay? This is something which at that time was a quite unusual concept. Not soil reinforcement, of course, but for earthquake foundation, earthquake engineering, it's quite new. And hopefully we can, and this is a place where research and practice are closely interrelated. Hopefully we said, okay, we know something on the seismic bearing capacity of foundation on soft soil. And these are mainly the studies we did with Jean Salençon after the Mexico earthquake, and that we presented in 1991. And on the other end, we know something about the behavior under static condition of nail structures. And again, this is the work which was published in 1993 by Professor Salençon and Patrick de Buan. So the idea is to say, okay, we have these two pieces. Let's try to modify them and to incorporate new ingredients that we need. And the new ingredient that we need is, first of all, to take into account the shear force contribution of what the soil reinforcement, let's say. And the second one, which is very important, is the capacity design philosophy. And for those of you who are not familiar with capacity design, so this is not something I invented. This is something I took from structural engineering, and it was, as a matter of fact, introduced by the New Zealand School of Earthquake Engineering with Professor Pauley in 1997. And I just took that idea and introduced it into foundation engineering. So the idea behind capacity design is the following one. This is a chain made of theoretical identical links. Let's imagine that the chain is your building, okay? And all the material here is common material which has a brittle behavior, just like concrete is a brittle material. So if you pull on the chain now, it will break somewhere, but you don't know exactly where. It could be any link here which will break when you reach that stress here. So the idea of Tom Pauley, in his word, is to say, okay, let's tell the structure how it should behave. So the idea is to say, okay, I will just replace in one place in my structure where it is convenient, where I can look at it, eventually repair it, and I will put a noble material here, which is a ductile link. So in that case, you will not have a brittle failure, but you will have some deformation which will accumulate. But this is not the end of the story. Then now, the other link, we will use the same, let's say, brittle material, but we will just give it a strength which is a little bit over that value. And in that case, you have brittle links, ductile link, and the end result is a ductile chain. So your structure, in case you exceed that value, will not fail. It will be damaged, and you know where it will be damaged. Okay? This is the idea of capacity design. So I just present the solution, and I will explain afterwards how we design it. So the final solution we designed for the foundation with soil reinforcement is to say, okay, under my foundation here, which is 90 meters in diameter, I will drive steel pipes, open tubes, which are 2 meters in diameter, 20 millimeters thick, and have a length of 25 to 30 meters. That depends on the depth of the soft materials, at a spacing of 7 meters by 7 meters. And this is a picture. You see the inclusions. You see the gravel layer here, which is 3 meters thick, and we just lay the foundation on top of it. Okay? This gravel layer plays an essential role in the system, and we will see in a few minutes. With that scheme, we have approximately 200 inclusions under each foundation. This is a cross-section of the foundation. You see the foundation, the inclusion here, 2 meters, 7 by 7 meters, the gravel layer on top of it, and the foundation, and the footing. And as you can see, it looks like a pile foundation, but it's not a pile foundation because there is no mechanical connection between the pile or the inclusions and the footing. Okay? Simply because we want the footing to be able to slide and even to uplift from the ground. Okay? Just to give you an idea of the size of one inclusion, this is one of the, some of you may know him, it's Ricardo Dobry, who was one of the checkers with Ralph Peck, and this is one of the inclusions that were put in place under the foundation. Okay? So, this is the idea. How did we design it? So, as I mentioned, I will skip all the technical issues here, and if you have questions, we can come back to that later on. This is the work we did with Jean Salençon with after the Mexico earthquake, where we calculated the seismic bearing capacity of foundation, taking into account the yield design theory that he developed with kinematic mechanisms that you can see here with possible uplift, rotation of the foundation, and so on. Okay? So, with those kinematic mechanisms, we were able to define a surface in the space overturning moment, shear force, normal force, and of course, soil seismic forces, which are not represented here. You can imagine that this surface is drawn from one value of the soil inertia forces. If you use another value, you will get another bounding surface, okay? Which means that if your overturning moment, shear force, or normal force are lying inside the surface, your foundation is stable. Of course, it's stable under permanent load, which is different from seismic load, but it's stable. So we have those results available. We just, based on the work again of nail structure, we just modify those mechanisms just by inserting the inclusion, taking into account the contribution of the inclusion, and taking into account the contribution of the gravel layer, which you see here, which is in between the inclusion and the footing. And I will show you how it works. So I will not use the surface, but I will make a cross-section through it, okay? I will make a cross-section, if I go back here, for a constant normal force, which would be a cross-section here, okay? So you have on that axis the horizontal shear force, and here's the overturning moment. Keep in mind the forces I indicated before, 600 meganewton for the shear force, 18 or 20,000 meters for the overturning moment. If we don't do anything, if we take the soil as it is in place, the cross-section of the surface of ultimate loads is the blue curve which is here. And you see that our forces are far above this value, which means that if, of course, if you apply these forces permanently, it will be totally unstable, but even under seismic action, where the forces are applied temporarily at few instants, it will create very large settlement, rotation, and so on. So what happens when we insert the inclusion? When we insert the inclusion, the surface just expands, and now the cross-section is here. And you see, in that case, we are quite close to what would be acceptable. But this is not the end of the story. Now the gravel layer, which is essential. If we put so this is the surface without a sliding surface, which is a gravel layer. If we put the gravel layer, the bounding surface will come like that, or the cross-section will come like that. And here, along this line here, sliding will take place. Okay? So how did we use those results that we developed on that occasion? First of all, let's come back to the capacity design. Capacity design, as I mentioned, I introduced that in the concept. And if you go back to the chain, what is the gravel layer? The gravel layer is exactly what I have called the plastic link, or what structural engineers call plastic hinge. And the reinforced soil is just the overstrength we provide to the rest of the structure or the rest of the system. And the combination of these two ingredients here, of course, they will bound the forces which are transmitted to the superstructure. They cannot be more than the sliding force, the weight times some tangent of the friction angle. And also they will control the failure mode, because we are sure that sliding will take place before tilting. Okay? So now we have to make the design. That are ideas. And we are obviously facing a new situation. And I remember the checker, Professor Peck and Professor Dobry, asking me, where has it been done before? And I had to say nowhere, of course. And so we decided to go step by step, slowly. So what we did, we first of all used those results I have presented here, based on the yield design theory, to make the conceptual design of the system, simply because it's very convenient for parametric studies. Then, of course, this is a model. And when you go to the physical problem, you have made a model, but you are not in reality. So we decided to validate the concept with model test. And I will show you the model test we run in a centrifuge facility. And it's only at the final design that we decided to go for very sophisticated tools. Of course, we could have gone from the beginning directly to these very sophisticated tools. But this is not a good idea when you are in a new design situation. You have to start slowly, just look at all the steps here. So at the end, we just make the final design with nonlinear finite element models. And for the seismic aspect, but I will not have time to develop too much about that, we develop something which will take into account the fact that loads are not acting permanently on the foundation, but are varying in time, which is what we call a dynamic macro element. I will just give you a few words for that. So the conceptual design. We use the yield design theory, and once again, this is the cross-section of my surface of ultimate loads for different inclusion spacing, 9 by 9, 8 by 8, 7 by 7. If you look at the pier, and if you assume, and it's very close to that, it's a 1 degree of freedom system. Almost it's very rigid. Then during the earthquake, you will develop inertia forces at some elevation, center of gravity. And if you look at the relationship between the overturning moment and the shear force at the base, it's a linear relationship, something like that. You have this proportionality between the overturning moment and the shear force V. So you will move along that line here. And we choose the inclusion spacing such that the line here intersects this vertical line here. In that case, we are sure that sliding will take place before. If the line were here, then you will get, of course, sliding, but also rotation. And remember that tilt was prohibited. So the inclusion spacing was chosen such that the line intersects the vertical line of our cross-section here. This gives us an inclusion spacing of 7 by 7 meters. Then we did some experimental validation of the concept. And we run centrifuge test, monotonic test, cyclic test. I will just show you one result of a pushover test, a monotonic test. So this is a view of the centrifuge facility we use. It's in Nantes. It's in IFSTAR, which is a new name of LCPC. It's a 5.5 meter radius here. It has a payload of 2 tons, and it can run at 100 G. Okay? So we use that one. We brought material from the site. We put, of course, scale inclusions here in the model. Here the size is, as you see, 90 centimeter. So we put those inclusions by hand. We put the foundation on top, and then we run the test until it fails. Okay? And if you compare the measured failure load in the test to what we computed with the yield design theory, you have these 4 values here. We run 4 monotonic tests, which are closely aligned along the line 1-to-1, which means that our prediction was pretty good. Okay? And this is, of course, it has many advantages. This is just a cross-section through the model when it has failed. You see here the inclusion after failure. Then, of course, the final design, we don't have access to settlement, deformation, and so on. We just know that failure will take place at some level of the forces applied to the foundation. To get access to the displacement in general, we have to use finite element model. Of course, we use the most sophisticated modeling techniques that we can with elastoplastic continuum element for the soil, beam elements for the inclusion, and interface condition with limited shear capacity and no tensile capacity between the raft and the foundation. So this is a view of the model. You see again the inclusion, nothing between the gravel layer between the inclusion and the footing. And again, just to compare the result to the yield design theory, this is a cross-section with our inclusion spacing of 7 by 7. This is without anything. And what you see here are the finite element results. So very close again to the yield design theory. So at the end, we have 3 ways of estimating the ultimate loads: yield design theory, experimental test, finite element analysis, and they are all within plus or minus, let's say, 15%. So we were very confident at the end on the result. Just to show you here a view of the deformed mesh, just to point out that the kinematic mechanism we have been using are very similar to what we computed with finite element models. Okay? Last ingredient in the system is this gravel layer, which should play the role of this plastic link. So it must be very pervious, because if it's not pervious, you will develop pore pressures inside and possibly liquefaction, so it has to be very pervious. So we define the required permeability from theoretical analysis, and it should have also an adequate friction angle, because if the friction angle between the footing and the gravel layer is too high, it means that you will not bound your forces. You will transmit larger forces to the superstructure. But it's too low. If it is too low, then you will get too much displacement. So we have to choose something which is quite adequate, and that was done with field tests. This is an example of a field test. This is a concrete block. This is the material we use for the gravel layer. We tested different materials. You have a jack here, and we just push on this block to measure the friction angle. And at the end, we found a material with a friction angle which was very stable, around 32 degrees for the friction between the concrete graft and the gravel layer. Very quickly about substructure interaction. So the idea here is to say, okay, we have a bridge which is 2.2 kilometers long. So if we want to model the soil, the pylons, the piers, and it will be too much. So we said, okay, let's take one pier here, the footing, the inclusion in the soil, and let's try to replace everything here by something that we call a macro element, which is, as a matter of fact, a two-node system connecting the footing, and this macro element represents the behavior of the foundation. Not only the linear behavior, non-linear behavior. So we did that. We developed a macro element. I don't have time to explain how, but we developed that macro element, and of course, we tested the macro element. If you look here, the two curves, the blue one is the one we computed with the finite element model, so it should be the best one we can. And the yellow one is the one we developed the macro element. You see how close they are to each other, even in terms of amplitudes and phase. So we were, again, quite confident to use those macro elements, and we put those macro elements under each pier in place of all the soil and inclusions. Okay? Finally, just a word on the tectonic displacement. Remember that the bridge has had to accommodate 2-meter displacement in any direction, which is quite a challenge between the piers. So this is a view of the deck without the concrete pavement on top, but you see the deck, and you see that it's only suspended by the cables. There is absolutely no connection between the deck and the pylon, and that is true over the 2.2 kilometers, which means that the deck is just a big swing, 2.2 kilometers long. Okay? Of course, you get vibration not from the earthquake. You have the wind, you have the traffic, and so on, and you don't want the deck to impact the pylon. So what was done here is to put a strut here. This is a stiff strut that will break when the loads are too high, which means that the strut is designed to take some loads, the wind loads, the traffic loads, without the deck moving. And then when the load of the earthquake is coming, it will break, and then the deck will be free to move. And of course, to prevent some impact, there are 4 dampers that are here that will dissipate the energy. And this is a view. We are just under the deck. We are here on top of the pylon under the deck. You see the strut is here, and you have 1, 2, 3, and the 4th one is behind me, the 4th damper. And we have this kind of system under each of the 4 piers. Of course, with a swing which is 2.2 kilometers long, during the earthquake, the displacements are very large, more than 2 meters at the extremity of the deck, which means that you need some special device here, and for example, an expansion joint, which is quite unusual, which is able to take into account this 2-meter displacement, and which was specifically designed for this bridge. The dampers also were specifically designed for the bridge, and if you want, I can give you some specification for the dampers later on. So this is the whole picture of the design. Now I will show you, because it's also very interesting, the process of construction of the bridge. So the idea was to say, okay, we will build, when I say we, it's Vinci, of course, it's not me. We will build the foundation, the footing, inside the dry dock, close to the side. And what you see here is a dry dock, which is 15 meters deep, which is, of course, you can imagine, 100 meters wide to accommodate one foundation. But the idea here is to put 2 foundations at the same time. So it's more than 200 meters long. And they built the 2 footings at one time. So you see here something. You have here to close the dry dock. The sea is just behind here. You have a cofferdam to close the dry dock. They built 2 footings inside the dry dock. Here you see, this is a dry dock. You see 1 footing, 2 footings, and you have the cofferdam here. Okay? When the first footing here has reached, okay, this is a view, so the cofferdam. In front here is the Peloponnese, Rion, and you see here the first footing, which is these beams here, and this is 9 meters high. You see the reinforcement of the raft. When one footing has reached a sufficient height to float, they just open the dry dock. The first footing is stored outside the dry dock, and the second one will come in the first place here and will close the dry dock, which means that they don't have to drive again sheet piles, cofferdam, which takes a long time. They will use the second footing to close the dry dock. And this is an aerial view. You see the second footing, which will come in front here, the first one being towed out of the dry dock. Okay? So you see now we are at another stage. That one is floating. That one is just closing the dry dock here. And the third one is starting behind. So with that process, they save a lot of time during the construction. Okay? And the first footing is floated to another place, not the final location, another place where it will be anchored to piles here. So here you see the footing. This is the footing here, 90 meters in diameter, towed by 3 ships here. It's anchored, and then construction proceeds. It's still floating to some elevation. Okay? This is, you see. Meanwhile, at the final location, they are driven the steel inclusions here with a barge, a specifically designed barge here. The inclusions are coming from the side with a barge. They are taken by this crane here and driven in the soil. And just to give you an idea, we have 201, 65-meter depth. They were driven at with an accuracy of plus or minus 20 centimeters. Then on top of it, they put the gravel layer, okay? And the pier, as a matter of fact, it's a pier now, was towed again to the final location. Then it was ballasted here. When it was, okay, now it's towed from the wet dock to the final location, and then construction proceed on site. Okay, you see here, it's at its final location, and now construction of the pylon proceed. And up to the top of the pylon where the cables will be anchored here. This piece here weighs 300 tons, and it was lifted in one shot from a barge. Okay? The deck is prefabricated on site, and then it's taken with the same barge and to the pier, and then it's added on which side, classical way of constructing a bridge here. And this is a view at some stage during construction. You have one pier which is completed with these cables. This one is completed. This one is under construction. You see the deck here. And this one is just starting here. Okay? And this is how you have seen this picture at the end. It's almost completed. 2.2 kilometers here without any connection, and 4 piers here. And the bridge was finished in August 2004. And there was a very high pressure for the Greek government to complete the bridge before the 8th of August, simply because, if you remember, it was the time of the Olympic Games, and the Olympic flame just crossed the bridge at that time. And so that was really, during this, let's say, I would say almost 10 years, it was a real adventure for all of us, all people involved in the design and construction of that bridge. And it was something we will remember forever. This is the Olympic flame here that will cross the bridge here. So if we try to draw some conclusion, what are the key factors? Because it was really a success. Nobody was injured on site. Construction was even faster than anticipated, and everything went very smooth. And if you look, what were the real reasons for that? First of all, we, all of us, made a correct assessment of what we expected from the foundation. At the beginning, the contract said the foundation should not slide, should not uplift from the soil, and so on. So we said, okay, it's impossible to build a bridge in those conditions. So we proposed sliding, uplift, and so on. So we made what we call a correct assessment of the foundation performance. You remember these 2 years between the signature of the contract and the start of construction. These 2 years were used to make the design. And this is very important because we were able, the design team was able to work without the pressure of the site. We were free to work, not without people waiting for your drawing, saying we are at that stage, we need absolutely the drawing of the next stage. So this is very important. And finally, there was a very close collaboration and also confidence between all parties who were involved in the bridge design. Of course, the owner, the contractor, the design team, and also the checker. At any time during the process, we kept the checker informed of our difficulties, our progress. And that was very important, just to help them to understand exactly what we were doing. Okay? So now to conclude my last question. How will the bridge behave during an earthquake? Because this is theoretical, and the real question is how it will behave. And it happened that in 2008, which is 4 years after completion of the bridge, an earthquake here struck the region of Patras, which is an earthquake with a magnitude 6.5, which is not a small earthquake, at a distance of, let's say, 35 kilometers from the site. The site is just here. And we have a lot of information on this earthquake. And we were very lucky because in the maintenance process, there is a survey of all the piers from time to time. And we had a survey a week before the earthquake. So we knew exactly at that time how much the bridge or each pier has settled. And of course, after the earthquake, we made another survey, and we know in that case that the foundation settled by 2 centimeters during the earthquake, which is nothing compared to the total settlement here. But more important, all the values that were measured after the earthquake were in close agreement with the prediction. Okay? And I will conclude with 2 movies which were taken during that earthquake. The first one is just, let's say, for, I hope it will. Sorry, okay. Okay, the first one is just a camera which is permanently there to monitor the traffic, and you will see the bridge moving. The peak ground acceleration measured on the deck was 0.4 g. And you will see the behavior of drivers. It's very strange. Okay, it starts moving now. So you see they are, not that one. Look at this one. You will see it's trying to keep his way here. And now look at these 2 here. The first one is just stopping because he is afraid, and they almost, the second one almost hit the first one, okay? Okay, that's just for journalists. Now let's look at that one, which is more interesting. We are again under the deck, and I launch the movie. This is the strut, and this is one of the damper. And when you will see the bridge, the deck is just on top here. Hope it works. Okay, the deck is moving. So at the beginning, you have, of course, displacement due to the elastic compression of the strut. Okay, and you will see at some time that one mechanical piece inside the strut will buckle, and then in that case, the strut will not act as a strut, and the relay will be taken by the dampers. You will see that. Okay. Okay, maybe I was not, no, I missed the, okay, I will start again. Comment on revient en arrière là-dessus? Okay, sorry. Okay, I will start somewhere here. Okay. It works? Okay. It should work. Okay. Now, and you will see at some time, no, it doesn't, I don't know why. Okay, I'm sorry, it doesn't work anymore. So at some time, it's very obvious. Maybe you have seen it, I missed it, but you have seen that this piece here of the strut did not work anymore, and the relay was taken by the damper. Okay, so this is, no, okay, I will see after. Okay, and okay, so this is the end of the story I wanted to tell you, and okay, well, something strange. You don't have the same thing as I have here. I'm sorry, I have to open it again because something strange is happening. Okay. So this is the end of the story, and this is if you go to that bridge, how the bridge looks at night. And I like this sentence here because it's not from a civil engineer, it's from a biologist, Louis Pasteur. And this is typically the situation we are facing almost every day in exceptional projects. We have to find a solution, and we have to rely on science. But of course, we don't have everything ready for us, and we have to do what we can with all the information we have. And with that, I thank you very much for your attention.
Thank you, Professor Pecker. It's really brilliant talk. Yeah. So now we can open for a Q&A section. Oh, please, Ms. Wang.
Okay, thank you very much, Professor Pecker, for the wonderful and enlightening lecture. And I do have a question about the finite element analysis. You mentioned there's a 2-meter horizontal sliding. Does that include in the finite element, or is just basically design criteria?
2 meter is a design criteria.
Okay.
And when we made the calculation for the design seismic motion, we calculated something of the order of 25 centimeters to 30 centimeters.
So that is just under the extrinsic loading that you anticipate as a 2-meter horizontal sliding,
but
which is not...
It's due to tectonic displacement, not to vibratory ground motions.
Okay, because I was quite curious if that included how to run the finite element analysis.
No.
Okay.
In the finite element analysis, we computed between 25 and 30 centimeters.
Okay, great. Can I ask another one?
Sure.
Oh, sure. Okay, so you rely a lot on the ground improvement using the steel pipe and also the gravel layer, but it's under the deep water.
Yeah.
How to do a quality control or the quality assurance during the construction and after the construction?
During construction, it was done. Okay, I did not mention that. Yes, I mentioned that the inclusion was checked. The location of each inclusion was checked with a laser afterwards, and they were within, let's say, 10 to 15 centimeters from the exact location. And then when they laid the gravel layer, they made also measurements just to be sure it's a plane surface. And we have at most 5 centimeters difference between two locations. They made 6,000 measuring points under each foundation. After, it's difficult. Now you have the footing on top of the inclusion. You cannot make any maintenance or any survey of the inclusion.
Otherwise, there's a little bit.
And if your question is corrosion, of course, we thought about corrosion, but we were lucky here because there was before the bridge, there was an electrical cable at the bottom of the sea, and we inspected the electrical cable. It was there for a very, very long time, and there was absolutely no corrosion, nothing on top of it. No siltation, nothing.
Okay, thank you.
Okay, thank you. Any other question? Hey, please. One only?
One today. Okay, Professor, I would like to know that how do you said it's a new technique to accept the sliding. So I was kind of curious, how do you come up with this non-conventional idea? I would like to know this part. Yes, thank you.
It was not an easy task, as a matter of fact. We just, as I mentioned, the key factor here was to inform the checker of all our difficulties, because of course what I'm presenting here is the end product, but we faced some difficulties during the development. So we always keep them informed. We took them with us during the centrifuge test and so on. We explained, and at the end they were convinced. And I didn't mention, but this concept has been copied now on at least 2 other facilities, one which is the Izmit Bridge in Turkey, where COWI used exactly the same design, and also on a nuclear facility in France at Bugey, under a nuclear building, we use also the same concept. So now it's not a unique one. It has been copied 2 times.
Okay. And
It may seem strange that I ask a question to Alain Pecker, but I have a question. He doesn't know the question, by the way. When, in your opinion, what are the key, the hot topics presently in earthquake engineering? What would be the tracks for people to work on for research?
Difficult question.
Oh, sure.
I would say, okay, we right now in Europe at least, we are just revising our structural Eurocode, which is a seismic design code. And what we are asked to do is to simplify the way we need to design structure, to simplify and to make them cost effective. Because we know now how to design structure, and if you go to sites which experience earthquake, and if you look at the new buildings, usually they behave quite well. But it might be too expensive sometimes. So what we are trying to do now is, okay, we know more than 30 years ago, but we want to simplify the way people make the design, because right now, if you look at the seismic codes, it's sometimes very tricky, and not all the design office can do that. So we want to make them simpler and also more cost-effective. Now, technical points, there is no really something which is emerging from another.
Okay.
If I may ask a second one. So you mentioned the earthquake in Mexico City in 1995. By the way, we were there, but not 2 weeks after. Exactly 1 month.
It was 1 month, okay.
Day per day, exactly 1 month.
1
We
month
were
after,
there on
okay.
the spot. You see, that's it. Well, recently they had another one on the same day, but 32 years after. So what do you expect to get from the observations from this new?
I don't know.
new
I don't know yet,
earthquake?
because people are. There is a team from at least from everywhere. There are teams on site right now. Even from France, there is a team visiting Mexico City this week, as a matter of fact. I'm not expecting something very new. What I fear really is what we saw in '85, that many buildings were damaged and they were repaired very quickly, but not very well. They just put some painting and so on. So the new earthquake on a damaged building, of course, that would make a lot of damages. But I do not expect really something very new from this new earthquake. Just confirmation of what we have seen in that time.
But since people tend to build longer, much longer bridge, for example, like between Hong Kong and Macau, the bridge is so long.
Yeah.
Would it be more face more serious problem by the design something?
Problem will be, it depends, of course. No, I don't, from the structural point of view, I don't think so. It depends how many spans you have and what
Okay,
is
the
the
more
length of
spans.
one span.
Mhm.
What will make the things difficult is, of course, as usual, the geotechnical conditions,
Mhm.
depth of water, because for construction it's a real issue. But afterwards, for example, in Lisbon, in Portugal, the bridge across the Tagus River is, I don't remember exactly, 18 kilometers. I think it's 18 kilometers. Did not pose real difficulties, except the cable stay bridge, which has a longer span, but the other one, no.
Okay. Any question from the PhD student? Yeah. There are many here. It's about the corrosion. You mentioned there's no. Oh, there's a question.
Yeah.
Okay, I'm sorry.
Yeah, Professor, thank you for your very excellent, simple enough for a building structural engineer to
Yeah.
understand. Maybe I didn't catch your idea. I want to know more about, say, do you consider or taken any advice as to the post-severe earthquake repair or damage control, etc.?
Yeah.
And
Yeah,
could you
that was
give-
the objective, is to have something which is damage control and could be repaired after the earthquake. Yeah.
How about very severe damage, and then any scheme for
No,
repairing?
the idea here is that we will limit the damage thanks to the strut here and the dampers. That will limit the damage in the deck and the superstructure. And sliding of the foundation will also, since we have a very strict control on the friction angle, we know exactly what will be the forces transmitted to the structure. They cannot be more than the weight times the friction angle. And this is what is essential here. But for that, you need to allow the foundation to slide. If you have a fixed foundation, you can transmit any forces. here we know exactly the maximum forces that could be transmitted to the bridge.
It's basically a base isolation.
It's basically a basis.
Early version of base
Yeah,
isolation.
exactly.
And the struts will be repaired.
After the 2008 earthquake, the struts under the 4 struts under each pylon, one under each pylon, were changed, of course. Cost a lot of money, but less than repairing the bridge. And,
We still have time. Yes. Sure, sure.
Out of my curiosity, so how do you validate your design assumption of that 2 meter sliding? That will be, I think that will be the critical point for the whole design.
we do not. We do not take into account. We do not accept 2 meter slider.
But you're
sliding.
expecting 2 meter.
2 meter tectonic displacement, which is okay. The bridge, any 2 piers can move apart or in the vertical direction by 2 meters, but the deck is totally flexible because it's fully suspended.
No, I know, but how about the foundation and the pier?
Of course, after this,
That gravel layer that basically there's an interface between what you call macro element at the foundation level and the upper structure. There's a gravel layer, and that layer you anticipate some kinds of large horizontal displacement to enable your design philosophy to be somehow successfully implemented. But how do you check and make sure before it was constructed, then this idea will be somehow successfully implemented in the design?
only with the centrifuge test. That's the only way we could check it. And by analysis, of course. And,
of course, the real behavior demonstrated is very successful. Yeah.
yeah, we have to wait for a stronger earthquake because that one was not a very strong. It was a strong earthquake, but not as strong as the design one. But
Did they observe any kinds of horizontal sliding on the?
No, only at the deck level. But there was no sliding, and when we back calculate what could happen, given all the records we have, it should not slide at that level for that earthquake, of course.
Yes, please.
So, welcome to Hong Kong, Professor. And, maybe one comment and one question. The question is, the soil there should be quite liquefiable, isn't it? Should be silty, sand to sandy silt. And I understood that the pile system is to prevent against liquefaction for the top layers, isn't it?
Yes, partially it will prevent liquefaction.
What about below that?
Below, we took that into account. What you could imagine, it's not a continuous layer that will liquefy. They are isolated lenses, and we took that into account, but during the earthquake, the forces are mainly affecting, or the forces transmitted by the foundation are mainly affecting the top 20 or 15 to 20 meters.
Yes.
What happens below, we really don't care. Of course, that will induce some permanent displacement in addition to what we computed, but they will be limited because it's only isolated lenses. The only place where we had a real issue was on the, let's come back. There is one place we have a real issue on liquefaction, which is, okay, here, which is on the Rion-Antirion site here, where we have a lot, okay, here, we have a lot of liquefaction in the top meters, and we decided not to improve the soil here because it will be too costly, given the large volume here, and the approach viaduct here were on piles, and we designed the piles to take into account liquefaction and lateral spreading here. So they were very big piles, very long piles, and they were designed to take into account lateral spreading due to liquefaction. But this is the only place where we had real issues. And just a story, the original project, because this is not the whole story of the bridge, this is an idea that the Greek government had for a long time, and there was a first call for tender in '88, and solution was a suspended bridge that was proposed at that time with 2 anchor blocks, and we were lucky not to choose that one because one of the anchor blocks was just in this liquefiable material.
So I can, if I'm correct, because I am from Greece and I was student of civil engineering during the construction, so should be at least 5 prime ministers changing, or 6, from 88 to 2004.
Yeah, exactly. I remember one meeting,
yes.
we were with the consultant of the minister, and suddenly the meeting stopped because the government has changed.
So, yes, the government changed just a few months before
Also.
the Olympic Games, so the new government got all the marks, but actually it had a long story. But anyway, it was a very exciting time for engineers in Greece, especially the students, to learn at that time about this, and also it was for all the society quite, let's say, the most important infrastructure on the point of view of technology, but also the design was the revolution at that time for the local society, for example.
Thank you.
Interesting. Any other questions? Yes.
Thank you, Professor. I have a pretty weird question. I didn't notice previously, if you mentioned during that earthquake, did the foundations actually slide or not?
No, it did not.
It did not?
It did not.
Okay.
It should not. According to calculation, it should not, and it did not.
Okay. So it was designed to be slidable if the earthquake was more fierce, from my understanding?
It should be, okay, the friction coefficient, friction angle is 32 degrees, which corresponds to a tangent delta. It should be around 0.5 or something like that. So for peak ground acceleration less than 0.5 g, it should not slide.
Less than 0.5 g.
Approximately, okay.
Okay. So if there was a really strong earthquake, and so it will, like the base isolation of the earthquake mechanism will work, and it will slide a little bit.
Yeah.
And then in this scenario, have you considered, and if they were originally aligned, the 3 foundations or 4, and then after the earthquake, they will no longer be aligned?
Yeah.
And how will this be adjustable on the
you cannot push back the foundation into their original position.
Yes.
You will have to live with that. But once again, the deck is fully suspended, so it will just accommodate the displacement, and the bridge will not be exactly, but it should slide by 20 centimeters, 25, no more. So
okay.
within a span of 560 meters, you will not even notice that.
Okay, okay. Thank you very much. Thank you.
Oh, great.
Thanks, Professor. It's a very nice speech. I want to ask, because it's you designed this bridge, and during the construction, if anything under control or they made some difficult challenges, and another thing is that during the earthquake, did you worry about the bridge? Or you just think, oh, don't worry, that everything is under control, it's okay. So what do you think about this? Yeah, thank you.
I hope that everything will be under control. You know, there is a very heavy monitoring system, and with alert system and so on. And for example, when the earthquake occurred in 2008, if I remember well, maybe you know better than me, the bridge was closed for a few hours just time to make inspection. And there is a very sophisticated alert system, and we have a lot of records after each earthquake. And for example, I'm supposed to receive a message. There are 3 levels of alert. One which is managed by the site people. They will just inspect the bridge and say, okay, we can open. Another one where they will say, okay, we send the information to the design team, not only me, to the whole design team, and we make our evaluation from Paris, for example. And the third alert is that we have to go to the site very quickly. But nobody knows. You know, you have to be very modest in earthquake engineering, because I answered before that I do not expect new information from Mexico City, but from any earthquake you may expect something new you have not anticipated before, and you learn from that. It's a very new science, as a matter of fact, earthquake engineering. You know, the new generation of, let's say, reasonable code zero and so on dates back from 70 or something like that. So it's quite a new science. And we learn from any earthquake, we learn something, not maybe very important, but we cannot always predict everything. And something which is important also in earthquake engineering, it's not an absolute protection. Remember, I said, okay, we designed for that level, but there is 0.05% per year that this level be superseded. So we have to make our design to accommodate that. So this is the reason why we don't use brittle material and so on, because if you use a brittle material, if you exceed by epsilon the design value, it will just break. Here it will, we hope it will accommodate. And this is the beauty of capacity design, as a matter of fact, as introduced by the New Zealand School of Engineering.
Yes, please.
Thank you, Professor, for the lecture. And my query is about, can you elaborate us a little about the investigation, geotechnical investigation that has been carried out? Anything special or conventional?
Yeah, it's special because given the depth of water, we have to use a dynamic positioning ship to make the investigation. And we run under each foundation one deep core borehole, which is 100 meter deep, and several SPT tests, several CPTs, cone penetration tests, also dilatometer tests, and we took undisturbed, what we supposed to be undisturbed sample from the ground. We just made X-rays of the sample on the ship to be sure that they were undisturbed. Then they were transported to the lab, where we did again X-ray to be sure that they were not disturbed during transportation. And we run a cyclic test and liquefaction test and all classical geotechnical tests, triaxial tests and so on.
Thank you.
I cannot remember the total cost of the soil investigation.
Because most of the soil is sand and gravel,
yeah.
so it will be quite difficult to have undisturbed.
Yeah, hopefully it's quite layered. So the sand layers are interbedded with clay layers, so it makes things a little bit more easy to sample. It's not a pure sand layer. If it's a pure sand layer, it's very, very difficult, I agree. Yeah.
Thank you.
Yes, over there.
So, Professor, so the gentleman here just mentioned about some kind of human factors. So, it seems so that your whole way to solving this problem is through communication as well. So it solves a lot of problems. And what about how do you face this kind of human factors? Like the gentleman here just mentioned about six party changing this kind of situation. I do want to hear how do you face that kind of situation.
I'm sure I catch your question exactly. Can you repeat it?
So the gentleman here said that political party changes, and then you said that like stopping down meetings, and this kind of situation might affect the time for you to build the beach. So how do you face and solve this kind of situation? I think it's very important nowadays.
Yeah, just with patience. You know that the tender was launched in 92. And then the contract was signed in 97, simply because of these factors, and also time to discuss with people and so on. But once the contract is signed, everything is in the hands of the concessionaires. So we are not affected by these external factors in that case. But during that period, before the signature of the contract, of course, as I mentioned, we have to leave one meeting because the government just changed during the meeting. And then we have to wait until the new government was in place, and so on. But this is very common. I'm working on another bridge in Chile now. That bridge was starting in 2001, or the design, I mean, not the construction. And it was stopped in 2006 because the government changed. And now they just start again 2 years ago, new design and so on. This is common for very large civil engineering structures. It always happens. because it costs a lot of money and people are...
Oh, yes.
I have a question, but it is not to Professor Pecker, but maybe to the audience, because I'm wondering whether this idea of a gravel or sand layer as an isolation has not been used in some countries. I'm thinking of Japan, for instance, for temples. So maybe somebody can give me some information about that. I think I read something like that. Of course, it was not such a huge structure, but I think this idea was already used in the past, or maybe actually presently. I don't know if somebody knows about that. Apparently, no, nobody. Yes, yes, please.
Yeah, I visited Shenyang in Northeast Asia, China, Northeast China. Yeah, Shenyang city. A developer showed us a building, no lights. So similarly, base isolation using sort of sand and space, and they made a selling point, and not a technological innovation or something very, very high profile.
And without any reinforcement of the soil below, of course, because here we have two ideas: reinforcement and isolation. If I'm not
this
mistaken.
is typical of our discipline. We never invent something totally new. We just bring pieces from different parts. For example, this capacity design, I just took it from structural engineers, and the gravel bed, maybe it has existed somewhere else, and reinforced structures or reinforced soil is used for nail slopes and so on. So just taking ideas and trying to assemble.
Yeah. Oh.
Okay, Professor, thank you for your good lectures. And I have questions about the dampers or the cables used for the deck. Do you have any ideas or the monitoring system to check the performance of the cables or the dampers, something like that? Is because the time is find a way. The performance of the cable may be...
Yeah, unfortunately, I cannot give you an answer because I was not involved in the design of the cables.
Okay.
I don't know.
Okay.
I'm sure they were tested and so on, but I can't tell you.
Okay, thank you.
You have the answer? Okay.
Yes, just even though I'm a geotech engineer, but the design of the superstructure is also with very modern concept, displacement-based design.
Yeah.
Even if the earthquake exits, still there are many, plans. There is plan B. So it is not conservative design, it's just quite modern with the displacement-based. And at some point there was some cables of the bridge that got fire. Yes. And
two cables.
It was on the news, of course, everyone got panic, but it was not a problem at all.
No. Two cables were fired and nothing happened. They have to be replaced. And that's
Any other question? Yeah. If no, I think we have very, very good lecture today and also very good Q&A section. So if you still have more questions, you can stay here. We still have about 10 minutes before the lunch, so you can discuss right here. So let's give the final warm applause and thanks to Professor Pecker. Thank you very much.